Today, I want to tell you about a new deadlock detection approach for promises in task parallel programming languages. So first, let me tell you what I mean by deadlock in this talk. So you may be familiar with resource deadlocks, where a collection of tasks is unable to proceed on a system because there are only finitely many resources. And these deadlocks can be corrected at runtime by restarting tasks or carefully scheduling tasks so that the resources don't run out. But when I talk about a deadlock in this talk, I'm going to be referring to logical deadlocks. These are situations where there is a logical inconsistency in the program, where a cycle of tasks are all mutually dependent on each other to produce a value, and none of the tasks can logically proceed. There's no way to correct this kind of issue at runtime. It's a software bug. The only thing we can do at runtime is detect them and throw an exception. So in task parallel programming languages, there are many approaches to deadlock freedom, ranging from static analyses to dynamic analyses. And on the spectrum of constructs and primitives for synchronization, on one end, you have constructs that have a lot of structure, like async finish or futures. And the deadlock problem is fairly straightforward now to solve in that domain. For example, we know that async finish constructs are deadlock free by construction. That's proven. And we also have a few algorithms for dynamically detecting deadlocks among futures. But as you start to move towards less structured constructs like promises, where the programmer has a precise, more fine-grained control over the synchronization dependencies, you lose this structure that allows you to easily reason about deadlocks. And in fact, I'm going to make the case today that it's currently impossible to truly detect a deadlock among promises, but we're going to solve that in today's talk. So what we would like is to have a runtime support for detecting deadlocks among promises that will raise an immediate alarm when a deadlock forms. And moreover, we want to be able to do this with low runtime overhead. So what is a promise? If you're not familiar with it, you may know it by a different name. For example, in the Java language, a promise is called a completable future because it's a kind of generalization of a future. Essentially, it's a handle for a value that will eventually be produced. Any task is allowed to set the value of the promise. So unlike a future where a specific task is bound to producing the value for a future, any task can produce the value for a promise. And likewise, any task is allowed to call a get method to block and wait for the value to arrive. Notably, only one task is allowed to set the value for any given promise. It's typically a runtime exception if more than one task does so. And so that's actually an important thing to keep in mind, is that the programmer who's using promises generally needs to be aware of which task is intended to set which promise, since only one task is allowed to do so. So this example program here on the left, we have two asynchronous tasks running together, two promises x and y. The first task, T1, will set the value of x to 3 and then print the value from y. Meanwhile, the second task, T2, will set the value of y to 7 and print the value of x. So in pictures, we have these two tasks, which have put these two values into the promises, and they're obtaining the values from the opposite promise. Now, here's a slightly different example. In this example, the first task tries to get the value for y, and then turns right around and sets x to that value. And task 2 will instead attempt to get the value from x and put that value into y. And so our question is, does this program deadlock? And at first it may seem obvious that yes, of course it deadlocks. What I just described was a cycle where we have task T1 waiting on promise y, which doesn't have a value yet. It's going to come from task T2, but T2 is stopped waiting on promise X, which also doesn't have a value yet because it will come from T1. So we have a cycle, right? But it's actually much less obvious than this. You see this relationship between promise X and task T1, that T1 will eventually set promise X, is actually unknown at runtime. Because at the moment the deadlock occurs, task T1 is stuck at this get operation. We haven't yet encountered the set operation. And likewise, task T2 is stuck at a get operation before the set operation. So in the machine at runtime, there actually is not enough information to look at what's going on and see a cycle. The connection between T1 and X is missing, and the connection between T2 and Y is missing. So there's not enough information on hand to actually even meaningfully talk about a deadlock, let alone try and detect it at runtime. So here's another example that's even worse in some sense. We have a task which doesn't do anything. It just terminates with a note from the programmer that it was supposed to set the value of X. And task 2 tries to get the value of X. So the question is there a deadlock here? And the answer is, well, there's definitely no cycle. Even if you had total knowledge of every instruction in the program and could see what was coming, there is still no cycle, right? T2 is waiting on the value from X, but there's no instruction in the program to set the value of X. So there's not even a cycle here at all. So what do we do with a program like this? I still argue that this is a kind of bug with the use of promises. Okay, so we're going to call this kind of bug an omitted set, because in some sense there is an intention for task T1 to set X, but it omitted to do so. So the claim that I'm trying to make here is that promises, as it currently stands, are missing crucial information, right? We can't actually detect a cycle because edges are missing from the cycle. We don't know which task intends to set each promise. And likewise, we have this related bug, we're calling this the omitted set, which doesn't even have a cycle at all, but it still causes a task to block indefinitely. And so it's a deadlock-like bug. And what I want to do today is show you how to solve both of these problems. So we will add some semantics to the promise construct that allows us to keep track of the ownership. So a task will own one or more promises. Every promise will be owned by exactly one task at any given time. And the rule is that a task is required to dispatch or take care of all of its owned promises before it terminates. And either that means the task must directly set each of its owned promises, or else hand off ownership, move the promise to some other task. And the way we will accomplish this movement of promises is by adding parameters to the async keyword to specify which promises should be moved into the new child task at async time. And once we add this new semantics to promises, it then becomes possible at runtime to detect both omitted sets and actual deadlock cycles. So here's an example. This is the deadlock cycle example that I showed earlier. And now I will show you what kind of changes we are proposing to make to the language. So to start off, the root task creates promises X and Y. And the first rule of promise ownership is that if you create a promise, then you initially own that promise. Okay, so initially the root task owns X and Y. And now when we spawn off the first child task, we have annotated the async instruction with X as a parameter. What this means is that the child task is taking on ownership of X from the root task. So as soon as the async issues, the new child task now owns X, and the root task now only owns Y. So the child task will proceed a little bit and then get stuck waiting on a value for Y at this instruction, and we know that it owns X when it does so. That's the new information that we have. Meanwhile, the second task will be spawned, and we've annotated its async instruction with the Y parameter, which means that the second child will take on ownership of Y from the root task, leaving the root task with no owned promises. So that the last rule of promise ownership means that a task is allowed to terminate only once it no longer owns any promises. So the root task is allowed to safely terminate, and we will not raise any kind of omitted set exception when the root task terminates. So now the second task is stuck waiting on the value of x, and we know that it owns y when it gets stuck. And now you see we actually do have enough information for the first time to actually say there is a deadlock cycle here. So this graph that we've been wanting to have here really does exist in the runtime state. We know that task T1 is awaiting promise y, which is currently owned by task 2, while it is awaiting promise x, which is currently owned by task T1. So we have a real cycle. So this, for the first time, makes it possible to detect cycles among promises at runtime. We do this by anticipating the sets that are coming, thanks to the parameters on the async instructions. We anticipate a set for x here, we anticipate a set for y. So even though we haven't actually encountered those instructions yet, we assume they're coming, and that allows us to establish enough information to see the cycle. And again, if a task ever terminates without setting or moving all of its owned promises, then we'll raise an omitted set exception. Okay, so that's part one of our contribution, is adding these semantics to the language of promises so that we can actually talk about omitted sets and deadlocks at runtime. So then the next question is, so how do you actually go about detecting a deadlock cycle at runtime with this information? So at first it may seem like you can have a simple cycle detection algorithm that just traverses the owned edges and the awaits edges. Every time a task issues a get, we'll chase these edges to look for a cycle to see if the get should be allowed to proceed. And that's essentially how the algorithm works. But there is quite a bit of subtlety here in order to guarantee that the algorithm works correctly. So the thing to keep in mind is that promise ownership can change dynamically at runtime. So just because task T1 owns X now doesn't mean it will always own X. It may hand off ownership of X to another task. And just because T1 is awaiting promise Y right now doesn't mean it will always be awaiting Y, because Y might get fulfilled. So the question is, how do we do correct cycle detection? And so here's the gist of it. We go into more detail in the paper if you're interested. But there are two main questions to ask, which is, so what happens if, as we are traversing these edges in the graph of dependencies, what happens if promise X is moved from T1 to a new task? Now, the way we can detect that is, as we are traversing this graph, every time we traverse an awaits edge, we go back and double check that the preceding owned edge is still valid. Because once T1 begins to await Y, it is no longer possible for T1 to move X to a new child task at least until Y is fulfilled, because T1 has blocked on waiting on Y. So after you traverse an awaits edge, you go back and double check the previous owned edge, and if it is still the edge that you expected it to be, then you have established a dependence between promise X and promise Y that is irrevocable. Nothing can happen that will break that dependence. It is always going to be the case that X cannot be fulfilled, at least until Y has been fulfilled. So that will give us some correctness in that case. The other question you want to raise is, so what happens if, as we're traversing this graph of dependencies, what happens if Y becomes fulfilled? What happens if the task that owns Y sets Y? We don't want to raise a false alarm. So what we do is that if we ever encounter a promise that's already been fulfilled, we abandon the cycle detection and we allow the original get that we were verifying, we allow it to proceed. We allow T2 in this case to block on X. Commit to letting that happen. Why is that a correct thing to do? Well, if a cycle truly is forming, then we will still detect it eventually, because at least one of the tasks will essentially be the last one to arrive at the cycle. And when it issues the cycle detection algorithm, that last task to arrive will detect the cycle and raise the alarm. So this is a very nice and elegant algorithm. It doesn't have any locks. There's no waiting. There's no retry loops. It's just cycle detection with a little bit of extra care to double check this owned edge. And anytime you encounter a promise that's already fulfilled or a task that's not awaiting any promise, then you can safely abandon the cycle detection and say that the get you are verifying is allowed to proceed. We have a full proof in the paper that accounts for all of these cases very carefully and proves that this approach will raise an alarm when and only when a deadlock cycle forms. So it's not possible to have a false negative or a false positive. And then another aspect of this algorithm that is very nice is that you can get it to work even under a weak memory consistency model. And we show exactly what the requirements are to get the proof to go through. There's just a few memory accesses that we need to be able to reason about in a certain way. And we show exactly how you can do that in the Java memory model, the C memory model, and the TSO total store. So if you're interested in the details of this algorithm and why it's correct, please see the paper. So the last question that we have is, so now we've added ownership semantics to the language. We've come up with an algorithm for doing deadlock detection, and the ownership semantics also give us omitted set detection for free. The question is it fast? And is it low overhead, both in terms of execution time and memory usage? So to test this out, we used a suite of 9 Java benchmarks representing a variety of algorithmic styles, all using promises in different ways, sometimes using them as if they were futures, sometimes using divide and conquer recursion, iteration, dynamic programming, many different ways of using promises. So we ran these Java benchmarks on a 16-core machine with an unbounded thread pool. And what we were looking for is to run the original program and get a baseline execution time and memory usage measurement. And then we enable our change to the promise semantics that allows us to annotate every async with the moving promises. And we enable detection of omitted sets. So every time a task terminates, we look to see if it has any outstanding owned promises. And we enable our cycle detection algorithm, which runs every time a get is issued in the promise. We'll see the verified execution time. So these are the results. The geometric mean over all the benchmarks of execution time overhead is 12%. Memory overhead is even better at 6%. This graph here shows the execution times baseline and verified runs of the programs. So as we can see, the overheads are low. So all of these programs do not exhibit deadlocks or omitted sets. So these are all correct programs. And so these are the overheads that we incur when verifying a correct program. Again, our algorithm is provably correct and precise, so there's no chance of false positives or false negatives. And so these are the overheads when you enable our detector. So in conclusion, we've done 3 things for promises. We've first added ownership semantics to how promises work. This allows you to associate at runtime to each promise the task which currently owns it, which is the task that is responsible for either setting it or moving it to some other tasks that will set it. And what this does is it reintroduces into the language missing information that is in the mind of the programmer who's thinking about which task is supposed to set each promise, putting it into the language itself so that it is accessible at runtime. This allows us to immediately assign blame for omitted set bugs. If a task terminates while it owns any promises that haven't been fulfilled, then we raise an alarm. We say that task was supposed to fill these promises. allows us to detect cycles at runtime. Because we have this ownership information, our cycle detection algorithm can traverse the alternating chains of this task is awaiting this promise, which is owned by another task, and so on. So we can do runtime detection of both omitted sets and deadlock cycles. We can do it with low execution time and memory overheads. And we go at great length into detail at great length in the paper about this cycle detection algorithm, proving that it is correct. It only detects cycles when they exist, and it will detect every cycle. And we show how it can work under a weak memory model in C, Java, and Total Store. Thank you.